Hello, my name is Paweł Czapiewski. Nice to be here. Thank you for inviting me. Can you confirm that you see me and my slide as well? Yes, we can. Fantastic. So, one sentence about myself. My name is Paweł Czapiewski. I'm employee in SII, outsourcing company that we support customers in various domains. We have one shop in almost any technologies that you can imagine. Myself, I have coming from Competency Center embedded. So we are building software that is intended to running on specific hardware with a lot of constraints from memory, resources, and so on. Sometimes even software that we created, which I'm personally interested in, is related to safety critical aspect, meaning if there's a error in source code, somebody will die. Also, my hobby is artificial intelligence. My talk about right now will be related to this topic as well. And beside that, I'm also a lecturer on one of the private university in Gdańsk, Polish Japanese Academy of Information Technology, where I'm trying to teach students as well of tools of artificial intelligence. So. Today we will talk about a specific use case about how solve hunger problem in world. I believe that one of a viable solution for that will be teaching how to produce our food using artificial intelligence. I will talk a little bit about our project that is trying to provide such a solution for such a concept. So we'll be talking briefly about hydroponic plants, the way of producing food that was utilizing this project, and tell it a little bit about artificial intelligence algorithms utilized in this project, and also I will show you a real life demo, which is actually with me here, the project that we created as well. So the world of plants is actually fantastic, full of mysteries and secrets. For instance, we know that it's proven beyond doubt that some plants have memory. There are scientific experiments that are showing that plants can remember the influences. A famous example with Mimosa pudica is famous plant. If you touch the plant, it will hide itself. So to protect, in order to protect from a shock or touch, whatever. But scientists proven that the plant itself can remember the type of influence that was coming, the type of shock, whatever, and ignore those one that the plant learned that is not longer any problematic here. That's wonder how it's working. We don't know yet. Another mind-blowing example is that we know that the plants, for instance, grow better if you're playing the music for them. There are scientific papers again proving that, and even one of the popular commercial series called Mythbuster was trying to play with this as well. So they created experiment. They built it 7 greenhouses, and they put a salad inside each plant, some kind of plants, and they actually one was for reference, one was playing recorded voice with positive feedback. A very good plant, you are growing very fast. Good job. The second one was a recorded voice, but negative feedback. You are the worst plant in the world. You are growing very bad. You are the worst possible being. Then they have also classical music and a death metal playing to the plants. And they find out that actually there is an influence on that. There's the difference to that. Death metal was actually the best way of providing feedback to plants. But we don't understand what was the root cause. So probably, of course, not the music itself, but the vibration of the air changing the pressures. But the mechanism itself is still wonder, a secret. So in this talk, we'll try to build algorithm that will try to find out optimal solution for this problem. So the project that we are dealing here is will be utilizing hydroponic technology. So that's a very growing market. In future, probably you will be producing the plants in this way. Last talk mentioned about the problem in the water supply. It is actually happening that we using more and more water, and we need more and more. This is actually way of preserving that, because you are closing the growing the plants in closed loop environment. We can instead of pushing the water back to the rivers and the sea, clean it and reuse again here. So the plants itself in such a system are grown without the soil. It's just put it inside the water, and the all nutrition are coming directly from the water here. A very growing market. We already have a lot of such a commercially available product that is producing our food in such a way. You can also then reduce transportation costs. You can just create them locally and so on. So in our project, we're trying also to build such an environment, but slightly different idea was in our mind. We would like to create a simple closed environment where we would like to control some parameters of environment in order to optimize this process of growing plants. So that will be the future. The scientists have even more interesting idea. So instead of hydroponic, they even try to next iteration will be aquaponic. Growing food in aquaponic means that we have, instead of one tanks, we have two of them, and one is containing the plants that you want to grow. The second one, there are fish, and actually the waste that are produced by wish is actually perfect source of nutrition for plants. So you're actually circulating water in this way. There are already some places in the world that are producing the very tasty plants in this way. But let's focus on the hydroponic part. So we have water, and we want to optimize that. How we can do that? So of course we will be. It's quite complex topic, quite complex, meaning there's different influences that we don't know what is optimal solution here. So here we'll be trying to find out some of the artificial intelligence algorithm that is capable of solving those problems. So it will be if you divided the trends in AI, it will be some kind of in maybe general AI trying to find out optimal solution for this problem here. So of course, it's quite complex in terms of finding possible solution. It will be as a black box. We don't know what is close relationship, what is the relationship between input and output. It will be treated. We don't understand the cross of why the solution was found in this way, but we hope that artificial intelligence will be providing to find solution by himself. So we have three different kinds of algorithms here, typically used: supervised learning, unsupervised learning, and reinforcement learning. We know about supervised learning, where we have neural networks where we can try to extract the knowledge from data that we have. We have labels to the data. Unfortunately, it's not a viable solution in our case, because we don't have any data yet. We don't know how to grow plants in this stage yet. Of course, we have supervised learning, where in this case we have also a lot of data, but not with corresponding labels. So again, it's not a viable solution for our use case here. So instead, we'll be using a reinforcement learning. So in this approach, we will be trying to find a model. The reinforcement learning is typically modeled by a Markov decision process. So the state that we are right now is depending only on current stats. Don't need a history of that. So that's the basic implementation of reinforcement learning algorithm. If you want to see that context in comparison with other solutions, so reinforcement learning would be perfect to find some kind of optimal policy, how to react with our environment. So we have the box environment is controlled by us, and we want to find out optimal solution. Do I need more lights? Do I need more water? Do I need more nutrition? And of course, they are closely related to each other. What is optimal strategy? Reinforcement learning should find out by itself. You don't need any data. That's the advantage of this approach. So what is the trick here? Reinforcement learning was famous again when it beated the human player in with Go game. It was one of the last bastion where artificial intelligence was still capable of losing with a human. Because if you compare this game with a chess, it's quite computationally expensive, because in chess the number of possible move or combination is reasonable. You can just create a huge tree of all of the possible combination, just traverse it, find the winning nodes quite easily. But the Go game was quite complex, even though we have two types of peons here, but the number of combination was growing exponentially. So human was quite safe. It was difficult to build the machine competing with a human. That changed when there was AlphaGo here created. AlphaGo was using reinforcement learning algorithm for finding out the best solution for the problem. So it was actually learning by themselves, by interaction with our environment here. So the idea is following here. We have an intelligent agent that is trying to perform some kind of action. I'm moving this point from left or right and so on, and it is interacting with environments. In case of game, the environment, of course, the boards and the position of all items on them. Then we have observation. So we get feedback to agent, and the part of this observation is a reward signal. So we are providing a feedback to agent. You are doing good, or you are worst player possible here. So the idea is that we are providing reward signal for the solution that we want to find out here. So in our case, the reward will be provided when the agent is capable of winning the game. So what is nice in this approach is that you don't need any data, just interaction with environment, and agent is capable of finding optimal solution here. Another beautiful feature of this algorithm is that the reward can be delayed. You don't have to provide immediately answer, because of course the reward in our case will be provided when the game is over. And we start to use this approach more and more, also commercially available product as well. We are able to play the games here. We are able to control complex robots with this approach and so on. So AlphaGo was the first robot that was able of beating Curia, was the world master in the Go game. After the match, he mentioned that the AlphaGo is God, nobody can defeat him. So that's a quote that shows how powerful this algorithm can be. So what is nice here, the algorithm itself was finding out what are the rules that govern the process here. We don't have to provide any models to that. It can be model-free approach. We don't need to know anything about the game itself. Agent needs just reward, and we'll find solution. Reward or punish, doesn't matter for stick or carrot. It's just from mathematical point of view, it's just the sign plus or minus, and we're optimizing the reward that we want to achieve here. So it is very interesting approach, because sometimes the results are unexpected. Results can provide something that we did not anticipate. There's a famous video created by OpenAI before they before they created ChatGPT, they also were playing a lot with reinforcement learning algorithm, and they created a simulation of hide and seek game. A hide and seek game. So they created a simulation where they put multiple agents. Agents were playing hide and seek. A blue one were trying to find hidden player, red one were trying to hide. Sounds silly, but they provide also a certain obstacle in simulation, boxes, for instance, and then they enables the bots, intelligent agents, to have some kind of interaction with the box. The bot could move them or freely on some kind of closed environment. And then they put multiple agents together in this simulation. And this starts learning process. Of course, it took millions of iteration, but after that, the bots find out how to build a shelter. They find out very quickly that you can use the obstacle to block the doors, and they, without any hints, any indication from creator of the solution, they found out how to build more and more complex structure to protect themselves from hide and seek. Of course, the seekers were also clever, and they find out soon that you can build ramps, and ramps were used to jump out and find them nevertheless. So it was quite adversarial, complex process where they acquired knowledge that was not available for them. Later on, they even found out the bugs in simulation. They were jumping on the blocks, which was not intended by behavior. So it is very interesting case because it provides the agent to learn optimal solution, but also finding out some things that were not there maybe. So that's a very interesting idea. If you want to create this super intelligence that I showed on the slide before, finding out better in every case than human, that's possibly maybe the case here. So in our project that I would like to tell you a little bit more about it, we also trying to learn, teach the reinforcement learning agent. The project is called EVAA. EVAA stands for Ecological Vertical Agricultural Assistant. So we would like to build an embedded devices that is providing an environment to play with this agent. Again, we don't have any data, but we would like to provide him an opportunity to interact with our environments. Of course, on the beginning, it will be just a pure try and error. That's how this algorithm is created. But later on, it will start to reuse the partially knowledge and try to acquire it. What is optimal solution for this problem here? So the goal here is obviously also to reduce the resources here. So we not only will be providing him reward if it is growing very fast and okay, but also we are able to provide a small punishment whenever the resources are utilized here. So if you are using water, if you're using electricity, okay, fine, but every time you get a small punishment for that. So this way we would like to tend to have this solution optimal with not using too much resources, preserve them. The project started as in form of a competition organized by Intel. Intel have the competition for showing possible application of the devices that they're producing called field programmable gate array. So we started as a project there, and actually we're very proud to receive Iron Award in EMA region. So it was quite achievement here, and based on that we can start to extend this projects. Later on, we moved from FPGA to rather more user-friendly hardware because we didn't utilize so many performance that field programmable gate array enable us. But in nutshell, idea is the following here. So we have some kind of intelligent agent that is able to interact with our environment. Of course, we need to have some kind of actuators that are capable of controlling some of the parameters here. There's quite a complex set of features that are enabled here that are controlling one plans. It's obviously not sufficient for optimal for production, but in this case we want to focus on gathering knowledge. What is optimal solution here? Later on, we can move this knowledge to a big farm and make that more cost efficient, of environment friendly, and so on. Once we interact with environment, we need to get the feedback. The agent needs to have some kind of information about state of the environment. For that is obviously we need some kind of observer. It is relying on heavily on sensors that we created and use for measuring real physical parameters of our environment. So once we won the Intel award, he actually started to looking for additional source of income for the funding of for the project. So it was also utilizing the internal in SII. We have internal project called Passion project, which SII is providing funds for project created by particular intelligent engineers and helping them to grow the passion here. So actually build the team inside it and use internal this passion program for further funding of this project. So later on, it's driven more and more, and nowadays in CC embedded that I'm coming from, is used as a workbench project. So if engineer is waiting for starting the new one or commercial one, it can acquire some additional knowledge participating in the further development of EVAA project. So let's then dive deep into the details here. We mentioned that we have actuators and we have observers that we are able to measure. So it requires a lot of technology here. So we have some kind of master unit created with Python programming language, which is capable of data processing, controlling everything. It's capable of providing information to database, and it's providing implementation of learning algorithm as well. We have set of controllers, so they are created with typical microcontroller systems that are capable of real-time controlling some parts of our environment. So, for instance, we have different lighting system that we are able to control intensity of the lights. There are special, very powerful LEDs used for plant growing. They have specific colors that are dedicated for interesting for plants. So they have blue and red. Actually, the green one is not useful for them. We have a specific ventilation system that we control. As I said, we on the beginning there's a music important for plants, but in our case we don't want to disturb engineers. Rather than we just provide the fan that is we can control what is the airflow flowing through the device. We have elevators that LEDs that we install. They are on a moving elevators because the distance between light source and plants is also important here. If it's too close, then we will actually the heat produced by LEDs will burn the plants. If it's too high, it also is not good because plants will tend to grow higher instead of nice round shape here. So we measure. We also have some kind of pumps that are providing nutrition for the signal here. Of sensor that we can measure the pH of our hydroponic solution that plants is dive in. We can measure pressure, humidity, and so on. Also, important factor for us is a camera, because as I said on the beginning, agent is only capable when we have feedback for him, if we can provide him some kind of price, punishment or reward signal. For our purpose, we are using camera, which is in real time monitoring the plant growth. Based on that, we created some basic computer vision algorithm, which is detecting and estimating the plant size. Here's you can see the example of growing green salads, and we are creating just metrics for us, normalize relevant pictures counter, which is providing some kind of estimation how many biomass is there on a picture. The more green pictures, the bigger the bigger value will be, the bigger information for our agent is, okay, I'm doing good, the plant is actually growing, it's we have a nice visual feedback for that. We also try different approaches like waste of a plant, but it's challenging because some of the water solution that is used here, so that's an respiration of water, so that seems to be quite interesting. Later we developed that even more, so there's a automated detection of a plant using some of the typical computer vision algorithm providing image recognition, and that was also utilized by us. So we created a few iterations of a system. The first one was also capable of providing the robot's arm that were trying to weigh the plants and then move and automatically replace them. For visualization purpose and experiment purpose, we try to create simulation of our plants. The biggest challenge in this project is actually the time. In order to grow the plants, you need significant number of days. Actually, in our case, where we are using a salad, it takes up to 20 days before it is grown. So for us, we created also a simulation of whole environment. As you can see on the beginning, we have this hide and seek games. We actually use a modern graphical game engine for creating simulation for us as well, where you can see the first hardware version of a plant with moving robots that were actually dealing with the plants, and we could also, the benefit of that approach is that we can try to model a plant. There are already some extensive mathematical models of growing salad, and from rainforest learning agent perspective, it doesn't matter if I'm dealing with real world, I'm living the simulation, I'm completely fine. It's as long as I have correct reward signal. So our goal is to use this simulation to pre-train it and then do the rest of experiment inside the real world. So that's an example how you can try to create the models of the plants. They actually were changing the color. So if you are doing the bad things to salad, it will actually also change the color here. So we are able to simulating them with a specific blueprint that is utilized for controlling them. So that enables us to create the Python implementation of agent and play either with real world or simulation of the environment here as well. So then we build the full system here. So the 9 boxes that each of the separated environments, there's an elevator that you can move up and down. The material used here is very special. It's called Miller. It's used for dispersing the light source. So we make sure that we have a equally distributed light intensity. We have a pH sensor that is measuring what is the current pH of water that is plant is growing, and we have a set of peristaltic pumps in our system. So that was a 3D printed parts, very cheaply constructed, connected with step motors, and using silicon pipes we can actually push them and precisely provide and measure exactly how much nutrition would you like to put to the plant. So the same as our intestines in our bodies work. There's a peristaltic movement created for pushing the food out of our system. So the same we are using for putting the nutrition for our system here. Robotic arms was used for carrying the plants, but later on so that's the full example of one of the systems. Here you can also see the fan that is growing here. And there is also a dashboard used for visualization purpose, that we can have a lot of data we can gathering them inside our database system. Later on, here you can see the implementation if you want to dive deeper into mathematical part of reinforcement learning algorithm. So the basic version is quite simple. So the idea is to find the Q matrix. You can see here Q, which is basically a huge table that is that is showing what is optimal action depending on which state you are currently finding agent is finding in. So the S letter, and RA is action that you can perform here. So you basically are calculating reward and iteratively updating based on some parameters, learning rate. You can update the new Q value. So that's one of the very basic example of implementation of calculation, how this agent is working. Of course, nowadays it's quite popular, and we have more and more possible solution here. One will be to replace the Q matrix with actually the neural network itself. So trying to estimate what is a optimal policy from state and action, and we can utilize that as well. So after we created the first iteration, which is quite a huge box, we learned a lot of, and we started to build a smaller, more portable version here. So here you can see second iteration of our devices, where the hardware was restructured. Idea is here to stack them, to create more of them, and stack them one after another. You can build a whole wall of them, and they will be processing, learning parallel what is the optimal planned solution. We also created documentation from this process, and we describe it and send back to French Ministry of Education and higher universities, because they create a register of companies that are performed research and development activities. Since SII is a French-born company, so it was quite also important for us. Here you can see and proof that it was actually recognized by Ministry of Education that we are performing something what has a could be considered research and development activities. So the other very initiative that we are very proud of, that was also important milestone for EVAA growth, is was last year Helmholtz GPU hackathon, GPU graphical processor unit. So Helmholtz Institute is a Berlin located institute that has inside of his management is one of the biggest supercomputer used in Europe. They have machine that they have 4,000 more than 4,000 GPUs connected into one place. And they organized together with NVIDIA, organized an event where they were open to external researchers and engineers for helping them utilize their server. So actually you can see here on the left, upper left part, we are our teams that is also participating in this event. The goal was to simulate the plant and try to teach agent and into running parallel simulation. It was quite challenging, but we proudly managed to teach agent on 4 GPUs. So that's maybe not utilizing supercomputer yet, but it helped us to parallelize the process as well. So then next step is since we have multiple of them and they're coming to the cloud, we started to push information also to the cloud. SII is a proud partner of Microsoft, so we are that is natural cloud provider selection of cloud providers. So we actually are pushing some of data to analytics parts of the cloud. We are also using some kind of cognitive services. That's the name how they're utilizing that for instance for voice control. So now you can you are able to control some of the interaction with devices using your voice. So you don't need hands, and you can. That would be easier if you have let's say hundreds of the devices. So maybe I will then, since you see me on the screen, I will just try to show you maybe details how this device looks like. I said we are very proud of that. So now you can see that there's the heart of our embedded here. This PCB were actually created by ourselves here. One important part is this: you have camera connected to device, and this camera is gathered by Raspberry Pi. Here you can see that, and part of sensors connecting to actuators and connected to the sensors. Is a device here. Powerful LEDs are growing. The salad, you can see elevator, and that's another here. You can see the PhD sensor that is measuring the water here. And the back, you can see 3 containers that are providing the nutrition. So one is a water, one is a acid, because salad likes something that is pH is between 4.5 still is 6.5, and you can see the third bottle which will be used for providing nutrition. Always controlled by our peristaltic pumps that we providing to our parts. And then later on they moved to the plant itself here. Of course, for demo purpose, this one is plastic, but still we are capable of running algorithms here. So that's is the first steps that we are performing. Now, of course, the learning starts. It will take a lot of iteration, thousands definitely, but I hope that in near future we'll gather millions of funding and we'll be able to build hundreds of such devices, and then we'll be able to find out what is optimal solution for growing the plants. Later on, each of us will have such a device in home where optimally using as many energy as needed, not much, just enough water for this process, and you will be producing the food inside your house, not wasting energy for transportation, not wasting food. It will be reduced because you will be producing as much as you need. That, I think, is the future of that, how we are producing food. I think that's all what I could share. Thank you very much. And we have some time for questions and answer session. Do we have any questions? No, it's the time for asking them if we have any. So, if not, then thank you very much for your attention. If you would like to see our device on your hand, please visit us. We'll be able, we are on site and you are able to see your own heights, and we can talk about more if you're interested in that. Thank you very much. See you on later.